G'day chemistry students. In this video, we are looking at a bunch of different dot points, most of them covering 6.2. This concept is going to form the foundation of a lot of what we're going to be talking about for the remainder of the module. This concept of dissociation. What happens to an acid or a base, certainly a Bronsted-Lowry acid or base, when it is mixed with water. And that's going to have an implication on this idea of acid-base strength, but let's get into it. First off, I want to revise what dissociation is. Essentially, it's the breaking up of a molecule into simpler components. In this course, generally what we mean when we say that is it's breaking up into ions. So we've already seen that before when we look at dissolving ionic substances to form a solution. The water molecules come along, they surround the different ions, they orientate themselves in a way which will attract the positive and the negative ions that are in the ionic substance. They then separate and are dissociated. Similar thing can happen with acids and bases. It doesn't look exactly like this. Essentially, we can have an acid here with the hydrogen and the anionic component, and they split into their ionic charges. So when we're looking at dissociation for a strong acid, first thing that we can do is look at this general equation here. HA is splitting up into hydrogen and its anion. You'll see that I've said that it is an equilibrium here. Technically, you can have those ions reform into molecules, but for strong acids, or what we call a strong acid, essentially those acids will pretty much completely dissociate. To be considered a strong acid, you usually have to have over 99% dissociation. So we have an equilibrium which is significantly shifted to the right. That generally means in most contexts, you can assume that there's 100% dissociation. For a strong acid, you might even see a reaction equation with a single arrow instead of a double arrow to indicate that pretty much all of the molecule of the acid is dissociating and forming those ions. What we'll also find when we're looking at acids is that hydrogen can interact with the water that is present and form hydronium. Again, a heavy right shift. Pretty much all the hydrogen that goes into solution will form this hydronium ion, which sort of means that we can change up this general reaction equation that we've looked at before and say that, well, if we have HA in the presence of water, that hydrogen will donate onto the water, forming hydronium, and the anion will be left over at the end. We can sort of see this in our animation here as well. The acid particles come in, those hydrogens donate onto the water molecules. This one here first, forming hydronium, and the anion, just like we've indicated here in the general reaction. And as we've talked about before, the main thing about strong acids is that they completely dissociate or near completely dissociate. For weak acids, though, what we see is the same general reaction equation, the same idea that hydrogen will interact with water to form hydronium. But for weak acids, they only dissociate in small numbers. A lot of the acidic substance which is dissolved into the water won't actually form ions, certainly not all at the same time. And so what you have is this equilibrium where you have the molecular acid forming into ions and the ions reforming into the molecular acid. And the equilibrium is shifted towards the left. Generally speaking, there'll be more molecules than ions formed. And we can see that here, this equilibrium, this interaction where we have the ionization happening and then the reformation of the molecule. And that pattern sort of happens over and over again. You can see that in all of the molecules that are present here. For strong and weak bases, we follow a very similar set of rules. I'm sure that you're already starting to notice we generally explain what happens to acids first and say, well, the inverse happens to bases. So it's actually quite difficult to find diagrams like this to show what bases are doing, but hopefully we can imagine what's happening based on what we've already seen previously when we've looked at those acids. So same general kind of rules. Here, according to the Bronsted-Lowry theory, the base is the proton acceptor. So we have the base, we have the proton. That proton is picked up and it forms Hb+. Now, if the base is a strong base, again, what we expect to see is for the base to dissociate, split up into its ions, and have the basic component interact with the hydrogen, forming Hb+. However, on the flip side, if we have a weak base, what we expect is that only some substances will dissociate, Only some substances will interact with the hydrogen and form Hb+. Now, there are lots of common acids and bases. We've looked at some already. They can then further be classified into strong and weak acids and bases. So what you'll find is that a lot of the acids that you've worked with previously already are our strong acids, the ones that dissociate almost entirely. In particular, hydrochloric, nitric, sulfuric acids are ones that you probably handled the most. They are all strong. But there are also weak acids. Acetic acid here, also known as vinegar, is a really common one. You might see hydrofluoric acid getting thrown around as well. All of these guys are weak acids. General assumption is if you don't know that it's strong, assume that it's weak. There are a lot more weak acids than strong acids. You'll also notice here that it says that water is a weak acid, which might be a little bit interesting. We probably wouldn't usually think of water as an acid, but we've also already looked at some interactions here where we can see water acting as a base. In fact, it's accepting a proton. The same thing can happen with water where it donates a proton and can act as an acid as well. So we'll see here that water is a weak base as well. We'll talk about this idea of water being an acid and a base in a few videos' time, but for now, we'll just know that it's a common weak acid. We've also got this term here, conjugate acids. Again, a concept that we'll look at in future videos as well, but all of these guys are weak. For strong bases, you're generally looking at hydroxides being your strong base. Something like sodium hydroxide, for example, is a strong base. There are other hydroxides that are strong bases as well. There might be a couple of oxides that might be strong bases, but again, same thing. If you don't know that it's a strong base, it's probably a really safe assumption to say that it's a weak base. Ammonia being probably the most common one here. Water can also be known as a weak base, and then we also have these things called conjugate bases. Again, we'll talk about those in future lessons. Thank you very much, everyone. Next lesson, we are going to be looking at what those conjugate acids and bases are and talk about this concept of an amphiprotic salt. But until then, have a good one.